Have you ever heard of programming languages written in a grid?
What? A programming language written in a grid?
Yes, you heard me right. SPL, Structured Process Language, is an open-source programming language written in a grid, and it is specifically designed for processing structured data. We know that almost all programming languages are written as text now, so what does SPL look like? What are the differences of the code written in a grid? Next, let's take a closer look. What we are seeing now is the development environment of SPL, which does look a bit different. The middle part is the SPL code. Seeing this coding approach, we can't help but ask, what are the benefits of writing code in a grid? When we program, we always use intermediate variables, and we need to give them a name. However, this name is not arbitrary and usually follows certain rules, and it should also be meaningful. This can be a bit troublesome. But with grid code like SPL, there is no need to define variables. In the subsequent steps, the name of the preceding cell is directly used to reference the calculation result of that cell. For example, here the A1 means to continue to process the data based on the calculation result of A1. No need to define variables. This is one benefit of grid code. Of course, SPL also supports defining variables, and you can decide by yourself whether to use it. Defining variables is also very simple. There is no need to define variable types. It can be used as needed. For example, in this statement, cod equals a4.new, the cod here is a variable. We can also temporarily define variables and expressions and use them, such as, in the function, a1.group at o, the lowercase a is a temporarily defined variable. There is a problem with using cell names as variable names. After inserting or deleting rows or columns, the name, namely position, of the cell will change, and using the original name will be incorrect. So how can this problem be solved? Don't worry, SPL IDE has already considered this. We pay attention to these two cells, A12 and B14. After inserting a row, these two cell names automatically become A13 and B15, and the cells automatically change without manual intervention, still very convenient. And the grid code gives a very neat feeling. Because of the grid, the code is naturally aligned. In SPL, the identification of code blocks adopts a grid indentation method, such as the for loop from B12 to B18 here, without the need for any modifiers, which is very neat and intuitive. Moreover, when the code for handling fragmented tasks in a certain cell is very long, the code will only occupy one cell, which does not affect the reading of the entire code structure. It will not allow the code in a cell that is too long to be written out of the cell, and affect the reading of the code on the right and bottom. In contrast, the text code needs to be fully displayed without this benefit. And we can also notice that there is a folding button on the row where the for loop is located that can shrink the entire code block. This feature is also provided by many text programming IDEs, but when applied to grid programming, it will make the code more neat and easy to read. In addition to the above features, SPL IDE also provides comprehensive editing and debugging functions. Let's continue to take a look at this development environment. In addition to the code area in the middle, the upper toolbar provides various running and debugging buttons, such as run, debug, run to cursor, step in. There are also functions such as setting breakpoints and calculating the current cell, which can fully meet the needs of editing and debugging programs. Each time one cell is executed, the code positioning is very clear. Unlike textual code, there may be multiple actions in one line that are difficult to distinguish, and some statements that are too long may become multiple lines and difficult to locate. There is also a result panel on the right that is worth paying close attention to. Due to the use of grid-style programming in SPL, the results of each step are retained after execution, debugging. Programmers can click on a certain cell to view the calculation results of that step in real time, and whether the calculation is correct or not is clear at a glance. No manual output is required, and the results of each step are viewed in real time, which further enhances the convenience of debugging. Moreover, the set of SPL is multi-layered, which can adapt well to multi-layered data, like JSON, and achieve true grouping. We will continue to discuss this later. We double-click on a record. You can view the results of the second layer. Above, we introduced the characteristics of grid code. Writing code to grids may provide convenience for editing and debugging, but it does not simplify each statement. Let's return to the SPL syntax itself. We always use loops and branches when dealing with data, especially in complex scenarios, which is a fundamental part of programming languages, and SPL naturally provides them as well. In addition, SPL has many unique features, such as option syntax, cascaded parameters, and enhanced Lambda syntax. Every programming language has a large number of built-in library functions, and the richer the library functions, the more convenient it is for us to implement tasks. Functions may be distinguished by different names or parameters, as well as parameter types, but sometimes when it is not possible to distinguish by parameter type, it is necessary to add option parameters explicitly to inform the compiler or interpreter of the functionality you want to implement. For example, Java has multiple open options when operating files. Using options to control different functionalities of the same function usually involves treating options as a parameter and mixing them with normal parameters, which can easily lead to complexity in usage. Moreover, for certain functions with an uncertain number of parameters, it is not possible to use parameters to represent options anymore. SPL provides very unique function options, allowing functions with similar functionalities to share a common function name, and then distinguishing them through function options, achieving the implementation of function options, making it easy to remember and use. For example, the function of pause is to find the position of substrings. If searching from back to front, the option @z can be used. Ignoring lowercase can use the @c option. The two options can also be combined for use. With function options, we only need to be familiar with fewer functions. When using similar but different functionalities, we can search for corresponding options, which is equivalent to SPL dividing functions into levels, making search and use more convenient. Some functions have complex parameters and may be divided into layers. Conventional programming languages do not have a specific syntax for this, and can only generate multi-layer structured data objects before passing them in, which is very cumbersome. For example, the example seen here uses Java for join operations to do an inner join between the orders and employee tables. It can be seen that, when implementing join calculations, it is necessary to pass multiple layers and segments of parameters to the map, and it is difficult to read, let alone write. Let's do a little more calculations because there are often other calculations after the join is done. Here, let's perform grouping by employee debt and calculate the sum for orders.amount. I believe there is no need to explain the complexity of using these functions further, as friends may already have a deep understanding of it. By contrast, SQL is much more intuitive and simple. To achieve the same calculation, SQL can handle it in just one statement. SQL uses some keywords, from, join, etc., to separate the various parts of the calculation, which can be understood as multiple layers of parameters, but disguised as English will have better readability. However, the universality of this approach is much worse, and selecting specialized keywords for each statement can lead to inconsistent statement structure. SPL did not use the SQL method of using keywords for separation, nor did it require nested layers like Java. Instead, it creatively invented cascaded parameters. The SPL specification supports 3 layers of parameters, separated by semicolons, commas, and colons. The semicolon is the first layer, and the parameters separated by the semicolon are a group. If there are any parameters in the next layer within this group, they are separated by commas, and the parameters in the third layer are separated by colons. The previous join grouping calculation is written as follows in SPL. It can be seen that this writing method is simple and clear, without nesting, and there are no situations of inconsistent statement structure. Practice has shown that 3 layers are basically sufficient, and there is rarely any parameter relationships that cannot be described by this writing method. We know that Lambda syntax can simplify coding, and some programming languages have begun to support it. For example, for Java 8 and later versions, counting the number of empty strings can be written as follows. The Lambda syntax of directly writing function bodies at parameters can simplify the definition of anonymous functions, and is very concise to use. However, implementing some slightly more complex calculations may take longer code, such as grouping and aggregation based on two fields. In this code, all places where field names appear must be prefixed the table name, that is, table name.field name, and cannot omit the table name. Anonymous function syntax is complex, and as the amount of code increases, the complexity rapidly increases. Two anonymous functions form a nested structure, making the code more difficult to understand. Implementing a grouping and aggregation function requires multiple functions and classes, including grouping by, collect, collectors, and so on, which are highly complex and still not concise enough. SPL also provides Lambda syntax, and is more comprehensive in support compared to languages like Java. The above example is written in SPL here. Calculate the number of empty strings. SPL directly simplifies x.count to a.count x, making it more convenient to use. However, it doesn't seem much different from Java. Let's take a look at the implementation of grouping and aggregation. Do you see the difference? When grouping or aggregating two fields in SPL, there is no need to define the data structure in advance. The overall code has no unnecessary functions, and the usage of sum and count is concise and easy to understand, making it even difficult to notice that they are nested anonymous functions. Let's take another example. The array stores the sales revenue of a company from January to December. We can perform the following calculations. A2 filters data of even months, while A3 calculates the growth value of monthly sales. In this example, the pound and -1 in brackets are used. The former represents the current sequence number, while the latter refers to the previous member. Similarly, if you want to compare the next member, you can use the 1 in brackets, including the tilde, current member, symbol used earlier. These are all the special functionalities that SPL provides in enhancing Lambda syntax. With these symbols, complex calculations can be implemented without the need for additional parameter definitions, resulting in stronger descriptive power and simpler writing and understanding. Grid code, function options, cascaded parameters, and enhanced Lambda syntax are the unique features of SPL that make it look fun. But inventing SPL is not for fun. The goal of SPL is to efficiently process data. For this purpose, SPL provides a professional structured data object, table sequence, and on the basis of the table sequence, it provides a rich computational class library. SPL supports dynamic data structures, which enables it to have comprehensive structured data processing capabilities like SQL. In contrast, as a compiled language, Java lacks necessary structured data objects, making data calculations very cumbersome. It does not support dynamic data structures, and cannot be dynamically generated during the calculation process, so it must be defined in advance. Even after the emergence of Stream, there is still little improvement. These are all due to the lack of support from Java's foundation. SPL provides a rich range of calculation functions, making it easy to implement structured data calculations. Here are some examples, including but not limited to sorting, filtering, grouping, deduplication, join, and so on. And there are many more. For example, two-field sorting. The @t here indicates that the first row is read as the field name, and subsequent calculations can be performed directly using the field name. Negative client represents reverse order. Without affecting reading, the code can also be written in one line, making it more concise. Let's recall the previous example. Java requires writing two layers of nested and lengthy code when implementing two-field grouping and aggregation, which increases learning and usage costs. And the same calculation of SPL is like SQL. Whether it is single-field grouping or multi-field grouping, the writing method is the same. Similarly, the calculation of join and then aggregation in SPL is much simpler, compared to other high-level language codes. Similar to SQL, you only need to make slight changes to switch association types without changing other code, such as join at 1 indicates left join, join at F represents full join. SPL also provides a cursor mechanism to handle big data that cannot be loaded into memory, and the calculation syntax based on cursor is basically the same as in memory. Similarly, adding the @m option can launch parallel computing and fully utilize multi-core computing power simultaneously. With abundant data objects and class libraries, SPL not only possesses data processing capabilities similar to SQL, but also inherits some excellent features of high-level languages, such as proceduralization, making SPL easy to process data. The previous content covers features such as fun grid programming, option syntax, and comprehensive structured data objects and libraries. It seems that SPL provides structured data processing capabilities similar to SQL, allowing programmers to do a lot of structured data processing and calculations even without a database. So is SPL a SQL that doesn't rely on a database? Not really. SPL does not stop here. For structured data, SPL still has many advantages over SQL. In fact, in our actual business, we often find that many SQL statements are not easy to write, with nested-in layers and hundreds or thousands of lines everywhere. This type of SQL statement is not only difficult to write, but also difficult to modify and maintain, which can be described as long and bad. The reason for this phenomenon is due to insufficient or even no support for certain features in SQL. Here we will take a look at a few specific examples and compare the solutions of SPL. Based on the stock trading record table, calculate what is the maximum consecutive rising days of a certain stock. This is the way it is written in SQL. This SQL statement is nested into 3 layers. First, a window function is used to create an up and down marker. Note that the up marker is 0, and the non-up marker is 1. Then, by accumulating by date, the interval with the same up marker is obtained. If not up, the numerical value is different. Then, by grouping and counting according to the markers, the maximum value is calculated to obtain the longest consecutive up days. How do you feel? Isn't it very difficult? Doesn't it take a while to understand? This is not a very complicated situation yet. Writing or understanding is so difficult. This puzzle was once used as a recruitment test for the SPL team, with a pass rate of less than 20%, because it is too difficult. It was later changed to another way, giving SQL statement for applicants to explain what it is calculating, but the pass rate was still not high. What does this mean? It means, if the situation becomes slightly more complex, SQL becomes both difficult to understand and write. In fact, this calculation is easy to solve according to natural thinking. Just sort it in order by trading day, start counting with a counter, add 1 when encountering an increase, clear to 0 when encountering a decrease, and finally check the counter to find the max value it has reached. It's very simple. Why is SQL written like this? This is because the set of SQL is unordered, and members cannot be accessed by sequence number or relative position, and there is no ordered grouping operation. Although some databases support window functions to some extent to support ordered operations, it is still far from enough. For example, using window functions in this example is still difficult. SPL directly provides support of order, naturally supporting ordered operations, so that code can be written according to natural thinking. This is the implementation of SPL. Firstly, A1 sorts by trading day. A2 is a counter with an initial value of 0. Then, A3 begins to loop and compare with the previous day. If there is no increase, the counter is cleared to 0. If there is an increase, then add 1. At the end of the loop, the maximum value that appears in the counter is the result we want. It is completely consistent with the natural problem-solving approach, and with the support of orderly calculation and procedural approach, it is expressed concisely, easy to write and understand. We can also use the SQL approach to implement. By still utilizing the ordered nature, new groups will be generated when the conditions are met, that is, when there is no increase, so that each increase interval can be divided into different groups. Finally, the maximum number of group members can be calculated. Although consistent with the SQL approach, the level of conciseness expressed is completely different. Next, let's explore grouping calculation. Continuing with the previous example, we will break down the second implementation. Please note the results of A2's ordered grouping here. This is the calculation result of A2, and it is a multi-layer set. Unlike SQL grouping that requires aggregation, SPL grouping not only allows aggregation, but also can preserve grouped subsets for subsequent calculations on grouped subsets. For example, in this example, counting each grouped subset and then calculating the maximum value. SQL does not have an explicit set data type, and cannot return data like a set of sets. It cannot implement independent grouping and can only force grouping and aggregation to be calculated as a whole. Through these two examples, we can see the advantages of SPL in ordered computing and set computing. SPL has many other features that are based on a deep understanding of structured data processing. Discreteness allows the records that make up the data table to be used independently and repeatedly outside the data table. Universal sets support set of any data and participate in operations. Join operations distinguish three different types of joins that can be tailored to local conditions. The support of cursor gives SPL the ability to process big data. With these features, processing data will become simpler and more efficient. Next, we will talk about performance. Performance is an inevitable topic in data processing, and we naturally need to discuss it as well. Still using an example, find the top 10 from 100 million pieces of data. Writing SQL is not complicated, but it has the word order by, which means that all data needs to be sorted, and then the top 10 are extracted. Big data sorting is very slow, involving multiple traversals and data exchanges between inside and outside memory. If executed literally, the efficiency will be very low. In fact, there is a faster method for this calculation that does not require a big sorting, always keeping a set of 10 maximum members, and can get the result by traversing once. Unfortunately, SQL cannot describe such an algorithm. We can only rely on the optimizer of the database. For this simple top 10 ranking scenario, most databases can do the optimization in engineering and will not actually do the sorting, so they can get the result quickly. But if SQL becomes complex, the database optimization engine will faint and eventually have to execute slow algorithms. Find the top 10 in groups like this. There is a significant difference in the way this SQL is written compared to the previous example of getting the top 10 from the entire set. It requires the use of subqueries and window functions in a convoluted manner to implement. In such complex situations, the database optimization engine will no longer optimize and will perform a sorting, making it very slow. In actual testing, it was found that Oracle's calculation of the top n within groups is several tens of times slower than calculating the top n of the entire set. Originally, the performance should have decreased slightly by only adding a grouping operation, but the difference in actual test results is very large. This indicates that Oracle may have done sorting when calculating the top n within groups, resulting in a sharp performance drop, and the optimizer fainted. Let's take a look at the implementation of SPL. Due to the concept of universal sets in SPL, which supports sets of sets, and the aggregation operation of SPL does not require the return of a single value, we can regard top n as an aggregation operation that returns a set. Therefore, using the high-performance algorithm mentioned earlier, without the need for big sorting, the calculation always keeps a set of 10 maximum members, which can be done in one traversal, and the performance is higher. Moreover, whether calculating the top n of entire set, or top n in groups, the writing method is basically the same, and there is no need to write tortuously, which is simple and efficient. We know that software cannot change the computing performance of hardware, and it always takes such a long time for a CPU to perform 100 million calculations, but we can design good algorithms with low complexity, so that computers can perform fewer basic operations, reduce computational complexity, and naturally increase speed. However, just coming up with a good algorithm is not enough. This algorithm also needs to be able to be written, that is, to be implemented in programming language. However, due to theoretical limitations, SQL provides inconvenient data types and operations, making it difficult or even impossible to implement many high-performance algorithms. If the optimizer also faints, it will only result in low performance. So we say that algorithm implementation often becomes a bottleneck that restricts high-performance computing. In a sense, writing simply and running fast are actually the same thing. To run fast, you need to make high-performance algorithms write simple. This is also the significance of SPL in high-performance computing. If the implementation cost of high-performance algorithms is too high, for example, they can definitely be written in C++, but maybe in tens of thousands of lines, which makes it impractical. We can make another analogy. Legend has it that Gauss encountered a problem when he was a child, calculating 1 plus 2 plus 3, plus all the way to 100. Other students start with 1 plus 2 equals 3, 3 plus 3 equals 6, 6 plus 4 equals 10 as soon as they get the question and keep calculating like this. Gauss' method is very clever. He found that 1 plus 100 equals 101, 2 plus 99 equals 101. There are a total of 50 101, and in the end, 50 asterisk 101 equals 5050 is quickly calculated. After listening to this story, people will feel that Gauss is very smart, but it is easy to overlook another thing, which is that in Gauss' era, people had already invented multiplication. Without multiplication, even if Gauss is smart, he cannot do it that way. SQL is like an arithmetic system with only addition, and the code is lengthy and inefficient in calculation. SPL, on the other hand, is equivalent to inventing multiplication, with simpler writing and higher performance. SPL invented many multiplications. Some of the SPL algorithms are listed here, in which highlighted by an asterisk are all original inventions of SPL. With these multiplications, the computational performance of SPL can be fully guaranteed. Let's take a comprehensive case study on the issue of spatiotemporal collisions. Identify the top 20 mobile phones that have appeared the most frequently in the same time period, and location as a specified phone, with a data volume of approximately 25 billion rows. This is the implementation of SQL. We know that performing distinct operations on big data is slow because it requires preserving the traversed list of different IDs, as the next ID needs to be compared with the list to determine the next operation. However, preserving and comparing large lists is resource intensive, and the database is prone to crashing. This calculation ran on the fast-known ClickHouse, and a single node crashed directly. It took more than 30 minutes to complete with 5 nodes. In fact, if the IDs are ordered, there is no need to keep the large ID list when doing distinct, and naturally there is no need to compare with the list. The calculation is faster and the hardware resource requirements are lower. Let's take a look at how SPL of supporting ordered operations to implement it. This is the implementation of SPL, and we will not explain the specific meaning of the script. SPL utilizes ordered storage and ordered cursors, which can effectively avoid the issues mentioned earlier, and in the end, it runs in less than 6 minutes with just one node. Not only does it have faster speed, but it also consumes less hardware, achieving the effect of a cluster using one single machine. Experience another case of e-commerce funnel analysis. Users purchasing products on e-commerce platforms will experience a series of events, such as browsing, searching, adding shopping carts, placing orders, making payments, etc. Funnel analysis is to analyze the user churn rate at each step, which belongs to the typical multi-step grouping and orderly calculation. Here we provide an example of a 3-step funnel analysis, where after implementing it in SQL, we cannot get a result after running for 3 minutes on the medium cluster, 4-node, of Snowflake. After implementing it using SPL, it only took 10 seconds on a single node to run, achieving the aforementioned effect with less hardware and faster performance. Running at a speed of 300 km per hour doesn't necessarily require high-speed trains like the MPP database, but a family sedan like the Esprek SPL can also be used. Finally, let's summarize that SPL, as a professional data processing language, adopts a very unconventional grid programming approach, which brings convenience in writing, debugging, and other aspects. In terms of syntax, It also adds new features such as function options, cascaded parameters, and enhanced Lambda syntax, which makes SPL look interesting. However, these features actually serve data computing, which stems from SPL's profound understanding of structured data computing. This brings a fun feature to SPL, combined with unique high-performance algorithms, which can make data processing simpler and more efficient. Many cases of single machine matching a cluster can effectively verify the effectiveness of SPL, which can completely replace the functionality of SQL in data analysis scenarios. SPL is currently open source. Welcome everyone to download and use it.